US Physics Olympiad year 2015 USAPHO Final Exam. This exam consists of 6 problems, Part A 4 problems and Part B 2 problems. For each part they were given 60 minutes. Solutions for all problems you can find below this video in the reference of the description. If you want to check many other problems from US Olympiad or whatever, you can subscribe to this channel. Problem A. Consider a particle of mass m that elastically bounces off of an infinitely hard horizontal surface under the influence of gravity. The total mechanical energy of the particle is E, and the acceleration of free fall is g. Treat the particle as a point mass and assume the motion is non-relativistic. Question A. An estimate for the regime where quantum effects become important can be found by simply considering when the de Broglie wavelength of the particle is on the same order as the height of a bounce. Assuming that the de Broglie wavelength is defined by the maximum momentum of the bouncing particle, determine the value of the energy EQ where quantum effects become important. Write the answer in terms of sum of all, or G, M, and the Planck constant H. Part B. A second approach allows us to develop an estimate for the actual allowed energy levels of a bouncing particle. Assuming that the particle rises to a height h, we can write this equation, where p is the momentum as a function of height x above the ground, n is non-negative integer, and the h is Planck's constant. First, determine the allowed energies En as a function of integer n, and sum all of g, m, and Planck's constant h. 2. Numerically determine the minimum energy of a bouncing neutron. The mass of a neutron is this one in kilograms or mega electron volts per c square. You may express your answer in either joules or electron volts. 3. Determine the bounce height of one of these minimum energy neutrons. Part C. Let E0 be the minimum energy of the bouncing neutron and F be the frequency of the bounce. Determine an order of magnitude estimate for the ratio E over F, if only needs to be accurate to within an order of magnitude or so, but you do need to show work. US Physics Olympiad year 2015 USAPHO Final Round. Problem A2. Consider the circuit shown below. IS is a constant current source, meaning that no matter what device is connected between points A and B, the current provided by the constant current source is the same. Question A. Connect an ideal voltmeter between A and B. Determine the voltage reading in terms of any or all of R and the IS. Question B. Connect instead an ideal ammeter between A and B. Determine the current in terms of any or all of R and IS. Question C. It turns out that it is possible to replace the above circuit with a new circuit as follows. From the point of view of any passive resistance that is connected between A and B, the circuits are identical. You don't need to prove this statement, but you do need to find IT and RT in terms of any or all of R and IS. US Physics Olympiad, year 2015, USAPHO. Problem A3. Solution for this problem you can find below this video in the reference of the description. A large block of mass MB is located on a horizontal frictionless surface. A second block of mass MT is located on top of the first block. The coefficient of friction, both static and kinetic, between the two blocks is given by μ. All surfaces are horizontal. All motion is effectively one-dimensional. A spring with the spring constant K is connected to the top block only. The spring obeys Hooke's law equally in both extension and compression. Assume that the top block never falls off of the bottom block. You may assume that the bottom block is very, very long. The top block is moved a distance A away from the equilibrium position and then released from rest. Question A. Depending on the value of A, the motion can be delivered in two types. Motion that experiences no frictional energy losses and motion that does. Find the value AC that divides the two motion types. Write the answer in terms of any or all of μ, the acceleration of gravity g, the masses mt and the mb, and the spring constant k. Question B. Consider now the scenario when amplitude A much greater than AC, A critical. In this scenario, the amplitude of the oscillation of the top block as measured against the original equilibrium position will change with time. Determine the magnitude of the change in amplitude delta A after one complete oscillation as a function of any or all of A, μ, g, and the angular frequency of oscillation of the top block omega t. Question C. Assume still that amplitude much greater than AC. What is the maximum speed of the bottom block during the first complete oscillation cycle of the upper block? US Physics Olympiad, year 2015, USAPHO. Final exam. Problem A4. A heat engine consists of a movable piston in a vertical cylinder. The piston is held in place by a removable weight placed on top of the piston. But piston stops prevent the piston from sinking below a certain point. The mass of the piston is M equal 40 kg. The cross-sectional area of the piston is 100 square centimeters, and the weight placed on the piston has a mass of 120 kg. Assume that the piston around the cylinder and the piston is a vacuum, so you don't need to worry about external atmospheric pressure. At point A, the cylinder volume V0 is completely filled with liquid water at a temperature 320 kelvins, and the pressure P minimum. That would be just sufficient to lift the piston alone, except the piston has the additional weight placed on top. Heat energy is added to the water by placing the entire cylinder in a hot bath. At point B, the piston and the weight begins to rise. At point C, the volume of the cylinder reaches V maximum and the temperature reaches 400 kelvins. The heat source is removed. The piston stops rising and is locked in place. Heat energy is now removed from the water by placing the entire cylinder in a cold bath. At point D, the pressure in the cylinder returns to P minimum. The added weight is removed. The piston is unlocked and begins to move down. The cylinder volume returns to V0. The cylinder is removed from the cold bath. The weight is placed back on top of the piston and the cycle repeats. Because the liquid water can change to gas, there are several important events that take place. At point W, the liquid begins changing to gas. At point X, all of the liquid has changed to gas. This may not occur the same as at point C described above. At point Y, the gas begins to change back into liquid. At point Z, all of the gas has changed back into liquid. When in the liquid state, you need to know that for water kept at a constant volume, a change in temperature delta T is related to change in pressure delta P, according to delta P approximately equal 10 power 6 Pascal per Kelvin multiplied by delta T. When in the gas state, you should assume that water behaves like an ideal gas. Of relevance to this question is the pressure-temperature phase plot for water, showing the regions where water exists in liquid form or gaseous form. The curve shows the coexistence condition, where water can exist simultaneously as gas or liquid. The following graphs should be drawn on the answer sheet provided. Question A. Sketch a PT diagram for this cycle on the answer sheet. The coexistence curve for the liquid-gas state is shown. Clearly and accurately label the locations of point B through D and W through Z on this cycle. Question B. Sketch a PV diagram for this cycle on the answer sheet. You should estimate a reasonable value for V maximum. Note the scale is logarithmic. Clearly and accurately label the locations of points B through D on this cycle. Provide reasonable approximate locations for points W through Z on this cycle. US Physics Olympiad, year 2015, USA PHO, final exam. Problem B1. This problem is divided into two parts. It is possible to solve these two parts independently, but they are not equally weighted. Part A. An ideal rocket, when empty of fuel, has a mass mr and will carry a mass of fuel mf. The fuel burns and is ejected with an exhaust speed of VE relative to the rocket. The fuel burns at a constant mass rate for a total time Tb. Ignore gravity. Assume the rocket is far from any other body. Question 1. Determine an equation for the acceleration of the rocket as a function of time t in terms of any or all of t, mf, mr, ve, tb, and any relevant fundamental constants. Question 2. Assuming that the rocket starts from rest, determine the final speed of the rocket in terms of any or all of mf, mr, ve, tb, and any relevant fundamental constants. Part B. The ship starts out in a circular orbit around the Sun, very near the Earth, and has a goal of moving to a circular orbit around the Sun that is very close to Mars. It will make this transfer in an elliptical orbit as shown in bold in the diagram below. This is accomplished with an initial velocity boost near the Earth, delta V1, and then a second velocity boost near Mars, delta V2. Assume that both of these boosts are from instantaneous impulses, and ignore mass changes in the rocket as well as gravitational attraction to Earth, to either Earth or Mars. Don't ignore the Sun. Assume that the Earth and Mars are both in circular orbits around the Sun of radii Re and Rm equal Re over alpha respectively. The orbital speeds are Ve and Vm respectively. First question. Derive an expression for the velocity boost delta V1 to change the orbit from circular to elliptical. Express your answer in terms of Ve and alpha. Second question. Derive an expression for the velocity boost delta V2 to change the orbit from elliptical to circular. Express your answer in terms of Ve and alpha. Third question. What is the angular separation between Earth and Mars as measured from the Sun at the time of launch so that the rocket will start from Earth and arrive at Mars when it reaches the orbit of Mars? Express your answer in terms of alpha. US Physics Olympiad, year 2015. USA PHO. Final exam. Problem B2. The nature of magnetic dipoles. Part A. The Gilbert dipole consists of a pair of magnetic monopoles, each with a magnitude Qm, but opposite magnetic charges, separated by a distance d, where d is small. In this case, assume that negative Qm is located at z equals 0 and positive Qm is located at z equals d. Assume that magnetic monopoles behave like electric monopoles according to a Coulomb-like force F equal mu0 over 4 pi multiplied by Qm1 Qm2 over r square, and the magnetic field obeys B equal F over Qm. First question. What are the dimensions of the quantity Qm? Second question. Write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than d. Write your answer in terms of Qm, d, z, and any necessary fundamental constants. Third question. Evaluate this expression in the limit as d going to 0, assuming that the product QMD is PM is kept constant, keeping only the lowest non-zero term. Write your answer in terms of PM, Z, and any necessary fundamental constants. Part B. An ampere dipole is a magnetic dipole produced by a current loop I around a circle of radius r, where r is small. Assume that the z-axis is the axis of rotational symmetry for the circular loop, and the loop lies in the xy plane at z equals 0. First question. Write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than 0. Write your answer in terms of I, R, Z, and any necessary fundamental constants. Second question. Let K, I, R power gamma have dimensions equal to that of the quantity Pm defined above in part A3, where K and gamma are dimensionless constants. Determine the value of gamma. Question 3. Evaluate the expression in part B1 in the limit as r going to 0, assuming that the product Ki r power gamma equal to Pm prime is kept constant, keeping only the lowest non-zero term. Write your answer in terms of K, Pm prime, Z, and any necessary fundamental constants. Question 4. Assuming that the two approaches are equivalent, Pm equal Pm prime, determine the constant K in part B2. Part C. Now we try to compare the two approaches if we model a physical magnet as being composed of densely packed microscopic dipoles. A cylinder of this uniform magnetic material has a radius r and a length L. It is composed of n magnetic dipoles that could be either all Ampere type or all Gilbert type. N is a very large number. The axis of rotation of the cylinder and all of the dipoles are all aligned with the z-axis and all point in the same direction as defined above, so that the magnetic field outside the cylinder is the same in either dipole case, as you previously determined. Below is a picture of the two dipole models. They are cubes of side d much less than r and d much less than L, with the volume Vm equal d cube. First question. Assume that r much greater than L and only Gilbert type dipoles. Determine the magnitude and direction of B at the center of the cylinder in terms of any or all of Pm, R, L, Vm, and any necessary fundamental constants.